Welcome back. We're going to conclude our discussion of amines with a nice summary exercise over here. We're going to draw and name examples of a primary aliphatic amine, a secondary aliphatic amine, a tertiary aliphatic amine, and then a primary aryl amine. And then we're going to redo our primary aryl amine with an ortho-nitro group. And when I did that, I wanted to make sure that you show all pi bonds. How do you get p to become pi? Well, you overlap it with another p orbital is how you do it in chemistry, but I'm talking how do you do it in fonts? We need the symbol font. Symbol font. Actually, you should go to the letter T and then go up one. Yeah, that's the fastest way. There you go. So we're supposed to show all pi bonds. I want you to be able to draw a nitro group is what I'm trying to say. So 1A. And don't make your life hard. Why don't we just I just realized what we're doing now is reviewing what we know so far, and then looks like we don't get to our review today for the test, although this has got a lot of review in it. It's all review. Segment 4 is 2 small reactions that finish up chapter 23. So there's a primary aliphatic amine, and you can call it propylamine if you want to give its common name. Propylamine. Or 1-propanamine. That'd be 1A. And 1B. Let's want to make our life easy, right? Stick with our propyl theme. Put 2 propyls on there. Nope, missed. Dipropylamine would be its common name. Or, it's going to be an awkward common name, but that, or UPAC name, sorry. N-propyl dash 1-propanamine. Longest chain with the amine is the UPAC name, propanamine, 1-propanamine. It's on the first carbon. And there's a group on it, also a propyl. And that's 1B for us. And you know where I'm going with this. Should have copied the second one, huh? It's okay. Slows me down. You like that. So we have 1, 2, 3, 2, 3, tripropylamine. Or it's 1-propanamine. How do you say there's 2 propyls on nitrogen? Get your eraser out. Should have started from scratch. N, comma, N. Dipropyl, 1-propanamine. And it's 1C. And don't get fancy for 1D or E. An aryl amine. Let's do the simplest one. Go benzene with a NH2. We have to know its common name is aniline. Saw it both in chapter 21 and chapter 23. And that's aniline, or, I mean, you can call it aminobenzene. That's fine. And for E, we're just going to put a nitro in the ortho position, if I remember correctly. Same aryl amine with an ortho. That's what O stands for, ortho. All right, and it'll be orthonitroaniline, and we're supposed to draw it with all the pi bonds showing. That way you're also going to have to show formal charges. We need to know nitro is a very unique group. It's got adjacent plus and minus in a like a Zwitterion fashion. And this is orthonitroaniline. Or orthonitroaminobenzene. You don't have to use the O. 2-nitroaminobenzene. Should say it's 1 amino. Right there. And I think we've finished question 1. And we're supposed to predict the results of reacting each of your amines in part 1 with sodium nitrite in aqueous hydrochloric acid. Wow. Now remember, the aliphatic amines give a big mess. So I don't know the extent to which I want you to answer that. In terms of products, A, B, C, you'd get a diazonium ion in all of them. No, I take that back. Forget about it. Plus my 1A looked like a B to start with. My eraser's too skinny. Here we go. 1A gives a diazonium ion. This is question 2. You're going to get this intermediate right here. Which is a primary carbon that has an excellent leaving group. Anything that can happen to a primary carbon with an excellent leaving group will happen with the ingredients present. What are the ingredients present? Excess aqueous, there's water present. Hydrochloric acid, which means there's Cl minus present. You get some SN2 products because you have a excellent leaving group. So you get that. You get this. You might get some rearranged products to a secondary cation. Instead of a SN2, you get a secondary cation and then an SN1 after rearrangement. And you get some elimination as a side product as well. And we just affectionately call that the old dog's breakfast, don't we? There's a mess on the floor. Okay, that's the primary. Secondary. You can't form a diazonium ion, so it stops in the middle. This is secondary. Remember, secondary. And this was primary. And you get this N-nitrosamine. And in the primary case, you made nitrogen gas. You'd see bubbles. So if I asked you visually what you would see, you would say bubbles in the first one. I see bubbles. In this one, you don't get bubbles. You get a yellow oil. That's what happens to the secondary amines. And not good for you either. And C, you're going to get you can't even make a bond to nitrogen on this one. You just get the conjugate acid, 2, 3. When it reacts with HCl. And it dissolves. And it started insoluble. This would not dissolve in water in any way, shape, or form. Tertiary amines don't have hydrogens for hydrogen bonding, so they're not soluble. And then all of a sudden you pick a proton up and you are water soluble, so you'd see it dissolve. That's what you would physically observe. And in D and E, we're taking our aryl amine and reacting it with sodium nitrite and aqueous hydrochloric acid. The important thing now is it's aqueous and it's done at room temperature. So D, and I didn't edit the answer here. Thank you for being patient with me here. That was our answer for E. Taking those two, and we're reacting it with diazonium producing conditions. So you get an intermediate in each one. No, if this was a test question, I didn't ask you for the intermediate. I'm just putting it there to make it more illustrative for you. And you get the diazonium. Aryl diazonium. Down here, you get the aryl diazonium with an orthonitro group. Same story, though. And who remembers what happens if you let that warm up when water's present? Same result each time. You get a phenol. And in the bottom one, phenol, orthonitrophenol. And who wants to take a guess at this? I can ask questions that are not on the list up there. How about question 4? pKa's below. Because we should always review the pKa of a phenol. It's not a normal alcohol because the O- that you would make by taking the proton off, the O- can resonate with the aromatic ring. Brings it all the way down to 10. Here, I would at least expect you to say this, less than 10. Truth is, it goes quite a bit less than 10. I don't know the exact number for orthonitrophenol, but I'm thinking it's below 7. And I'm basing that on, this is a aside. A fascinating aside. Two, 4, 6 trinitrophenol. It's also known by a different name, picric acid, and its pKa is borderline strong acid. I told you, nitro groups have powerful inductive and resonance effects, and they lower that pKa right down there. And I'm debating whether I want you to learn that one. I don't know. I'll come back to you on that. And we had another part here. Place amines in 1 in order of increasing basicity. Well, we have them all on the screen here. We'll put, there's 5 of them. There's 5 of them, and we'll put weakest base equals 1, strongest equals 5. And our strongest base is right here. I'll put a circle on it so you know what I'm using the circles for. We'll explain why shortly. There'd be almost a tie between A and C. So I'll go for each. Primary and tertiary aliphatic amines have similar basicity. I don't expect you to distinguish them. And then I'll drop down to number 2 next. And that would be this one. Yeah, no 3 because 4 is tied. And the weakest base. It's a poor choice of numbering, isn't it? 1 sounds like strongest, doesn't it? Weakest is 1. And strongest is 5. Now you need to talk to me about conjugate acid stability. So this is my answer to question 3. See circles first for the order. Okay. And then talk to me about the conjugate acid stability. Conj acids are all N with at least 1 H and a plus charge and at least 1 propyl group. R equals propyl or H. R prime equals propyl or H. There we go. So for B, in B, there is the best combination of what 2 factors to stabilize this ammonium ion? In B, there is the best combination of hydrogen bonding there's 2 propyls in B and 2 H's in the ammonium ion. 2 H's and hyperconjugation. 2 propyls. In A, we had only 1 propyl, yet you're going to have 3 hydrogens. So you got a better hydrogen bonding situation, but a worse hyperconjugation situation. In C, you've got the best hyperconjugation situation, just think 2 propyls here, 3 carbons helping out the cation, but only 1 H for hydrogen bonding. When you have 2 and 2, that's the best combination. So that covers molecules A, B, C. And D, we're still on answer to number 3. Get it separated from everything here. AR NH3 plus found in D and E has lost resonance of N lone pair with aromatic ring. So that's gone. That was bad. Don't do that. That means they're very bad bases. Those are our worst bases, aren't they? Worst and second worst. And then you just have to say that when you make an N plus here, and you already have a molecule that has an N plus, that's going to be the worst situation. And I don't know what to see. I shouldn't draw my lines first. And got a little overzealous erasing too. Yeah. Okay, and turn my pen off. I've got a nightmare going on here. All right, so in D and E, this is D and E. In E, there will be 2 N pluses in the same molecule. And clearly that's not a good situation. That's why that one's the worst. 2 cations. It's a good spot to stop. And then we have just a short segment coming up where we're going to learn about 2 elimination reactions. One's called the Hoffman elimination, and the other's called the Cope elimination, and they both are amine reactions. So we'll be seeing that after the break, and I'll see you then.